Zero fires. Zero thermal runaway. Tens of thousands of charge cycles with almost no capacity lost. That is the certified performance profile behind a battery plant that just went fully operational in Xinjiang, China, storing enough electricity to power hundreds of thousands of homes for 5 hours straight. This is not built from anything resembling the battery in your phone or your car. It stores its charge as a liquid in tanks, pumped through a stack the way fuel moves through an engine. You heard that right. Rongke Power confirmed the plant's commissioning this year, built on technology developed at the Dalian Institute of Chemical Physics. Let me tell you what that actually means in plain English. You know the feeling of an old phone battery that barely holds a charge anymore. This chemistry was engineered specifically so a grid never has to feel that. And that is just the beginning. Hit a quick like and subscribe, because by the end of this video you will understand exactly how this technology is closing in on lithium's throne. For decades, if you wanted to store electricity at any serious scale, there was only one answer anyone took seriously. Lithium won that argument so completely that almost nobody thought to ask if it was the right chemistry for every job, including the one it was never built for. Lithium-ion earned its dominance, honestly. Pack an enormous amount of energy into a small, light container, and you can put it in a phone, a laptop, a car, anywhere. Weight and size matter more than almost anything else. That is a genuine engineering achievement, and it reshaped an entire century. But here's the detail that puts everything into perspective. Grid storage does not care about weight. A battery plant sitting on a fenced lot in the desert does not need to fit under a car seat. It needs to survive tens of thousands of charge cycles, sit safely next to a residential neighborhood for decades, and never once catch fire. Lithium was never optimized for that job. It was optimized for portability, and the industry simply carried that same chemistry into stationary storage because nothing else looked commercially ready. Think of it like building every bridge in the country out of the lightest possible aluminum, because aluminum happened to work brilliantly in aircraft. Weight was never the constraint for a bridge. Nobody checked whether that assumption still held. The same blind spot shaped grid storage for the better part of 2 decades. Utilities kept reaching for the chemistry that had already proven itself, because retooling an entire supply chain around something unproven felt riskier than living with the trade-offs everyone already understood. Manufacturing capacity, supply contracts, and engineering talent had all been built around lithium's specific needs, and that inertia is its own kind of ceiling, one that has nothing to do with which chemistry actually performs best in a given job. That mismatch had a cost. Grid-scale lithium installations degrade the same way your phone battery does, capacity fading year over year. And when something does go wrong, a lithium fire is extraordinarily difficult to extinguish. Utility operators absorb both risks for years because the alternative did not seem to exist. Insurance premiums on large lithium storage sites climbed as fire departments learned, project by project, just how differently these fires behave compared to anything in a standard emergency response playbook. Some municipalities began requiring wider buffer zones around new lithium storage sites, quietly adding cost and complexity to projects that were supposed to be simple additions to the grid. In 2000, a chemistry professor named Zhang Huamin joined the Dalian Institute of Chemical Physics and made a decision almost nobody in the battery world respected at the time. He built a research program around vanadium flow chemistry, technology that had been sitting mostly dormant since the 1980s, dismissed as too bulky and too expensive to ever matter commercially. Zhang's argument was simple and at the time unfashionable. Grid storage needed a completely different set of properties than portable power ever had, and chasing lithium's playbook was solving the wrong problem entirely. He was not trying to build a better version of the battery already winning. He was trying to answer a question the rest of the industry had not thought to ask. That decision would take 25 years to prove out, and what it eventually produced was not a slightly better battery. It was an entirely different answer to a question the industry had stopped asking. The chemistry itself was not new. Researchers at the University of New South Wales in Australia had demonstrated the core vanadium redox concept back in the 1980s. For nearly 2 decades afterward, it went almost nowhere. Industry consensus treated it as a curiosity. Too bulky for anything portable, too expensive to compete with lithium's falling costs, a solution in search of a problem nobody urgent enough to fund. Investment dollars followed lithium instead because lithium already had a booming consumer electronics market to fund its own improvement. Here's what most people get wrong about that dismissal. The bulk that made vanadium flow chemistry look hopeless for a laptop was never actually a flaw. It was simply irrelevant to a market nobody had built yet. Grid-scale storage, where a battery the size of a warehouse is not a design failure, it is the design. The industry had judged an entire chemistry by the wrong scorecard. Zhang's program at the Dalian Institute of Chemical Physics set out to solve the two things actually holding vanadium back: unstable electrolyte that degraded over time and stacked components too expensive to manufacture at scale. Neither problem had anything to do with the bulk everyone kept pointing at. They were solvable engineering problems, not fundamental limits. That distinction, solvable versus fundamental, is the entire reason Zhang's team kept funding a technology everyone else had quietly abandoned. They said the same thing about early solar panels: too expensive, too inefficient, a science fair project that would never scale past a rooftop demonstration. We all know how that ended. By the mid-2000s, Zhang's team, working alongside what would become Dalian Rongke Power, had a working stabilized electrolyte formula and a rough industrial roadmap. The skepticism from established battery manufacturers did not disappear. It just stopped mattering, one small pilot installation at a time. Each small deployment chipped away at the assumption that flow chemistry could never leave the laboratory. Utility engineers who toured the early pilot sites came away with a different question than the one they arrived with. Not whether the chemistry worked, but how quickly it could be built at scale. But a stabilized electrolyte and a pilot plant are still a long way from a grid operator trusting your technology with $1 billion renewable build-out. The mechanism that actually made this commercially real had not been revealed yet. And it is stranger than most people expect. Here is the problem. Lithium's design creates that almost nobody outside the industry ever thinks about. In a lithium battery, the amount of energy you can store and the amount of power you can deliver are locked together inside the same sealed cell. Want more capacity? You need a bigger, more expensive battery, full stop. Every additional hour of backup power means manufacturing an entirely new, larger unit from scratch. Picture a car with a fuel tank welded directly to the engine block, so the only way to add range is to build an entirely new engine. That is what every lithium installation is quietly doing. Vanadium flow batteries break that link completely. The energy lives in liquid electrolyte, stored in external tanks. The power comes from a separate stack where the reaction actually happens. Want more range? Add bigger tanks. Want more power? Add a bigger stack. The two are no longer welded together. Scaling a lithium plant means replicating the entire expensive unit. Scaling a flow battery means adding cheap tankage next to equipment you already own. This was the exact problem Zhang had been circling since 2000. The belief that grid storage did not need to inherit lithium's constraints just because lithium got there first. Decoupling energy from power was not a minor feature. It was the entire thesis his program had bet 25 years on. Every design decision his team made afterward flowed from that single structural choice made years before anyone outside Dalian was paying attention. The consequence is duration that simply is not available to lithium at reasonable cost. Rongke's 100-megawatt Dalian peak shaving station, connected to the grid in 2023, proved the concept at commercial scale. Years of continuous cycling with none of the capacity fade that steadily erodes a lithium installation's usable output. Operators running that station reported output holding essentially flat across seasons, in a way lithium sites simply do not. Decoupled power and energy is not a small advantage. It is the difference between a battery that ages and one that does not. Most people who read about battery breakthroughs never get to this part, the mechanism itself. And on its own, it still does not explain how vanadium became cheap enough to matter. That answer is stranger, and it meant betting against everything the industry assumed about how to win. Decoupling power from energy solved duration. It did nothing about cost, and cost was the real reason vanadium had spent 20 years as an industry footnote. Precious metal catalysts and brittle graphite components made early flow battery stacks expensive to manufacture and fragile to operate. Exactly the reputation that had kept serious investment away. A single cracked plate could take an entire stack offline, and replacing graphite components at scale was never going to be cheap. Here is where the consensus broke. Instead of chasing lithium's strategy of squeezing more energy into less space, Zhang's team made the opposite bet. Stop competing on energy density entirely and optimize for something lithium could never touch. Multi-decade lifespan with almost no degradation and a chemistry that is physically incapable of thermal runaway because the electrolyte is water-based and non-flammable. It sounds like it should not work, refusing to compete on the metric that made lithium famous. In a battery market obsessed with density, is exactly the move a team is not supposed to make. It worked because the team replaced the two most expensive components in the stack. DICP developed a carbon-plastic composite bipolar plate to replace brittle, costly graphite. Cheaper to manufacture, more durable in operation, and easier to produce at the volume a real grid build-out would require. The new plate could flex instead of crack, which alone cut both material waste and field failures during installation. What Zhang's team risked was years of institutional funding on a chemistry the rest of the industry had already filed away as commercially dead. Peers told them flow batteries would never outcost lithium's falling curve. They built anyway. The measured result: vanadium flow batteries operating in the field now demonstrate tens of thousands of charge cycles with negligible capacity fade. A lifespan measured in decades, not the finite cycle count that eventually forces every lithium installation into replacement. For a utility planning 30 years ahead, that difference alone reshapes the entire financial case for which chemistry belongs on the grid. Less energy dense, and it wins anyway. That is not a contradiction. That is the whole point. Two mechanisms working in a lab and even in a single 100-megawatt station is one kind of proof. Coordinating this technology across an entire province's power grid is a completely different order of problem, and that is where the real test was waiting. Xinjiang has more sun and wind than almost anywhere on the planet, and for years it wasted a staggering share of it. Renewable output routinely outpaced what the grid could absorb in real time, forcing operators to curtail, switching off perfectly good solar and wind capacity simply because there was nowhere for the electricity to go in that moment. Short-duration lithium buffering could smooth minutes. It could not touch a problem measured in hours. Engineers needed something that behaved less like a shock absorber and more like a reservoir. Now, here is the part that changes everything. In the county of Jimisar, engineers paired a 200-megawatt, 1,000 megawatt-hour vanadium flow battery system directly with a 1-gigawatt solar farm. A single coordinated architecture built to store 5 full hours of output and release it exactly when the grid needs it instead of when the sun happens to provide it. This is not passive storage sitting on standby. The system operates in grid-forming mode, actively stabilizing frequency and voltage for the surrounding network, acting less like a battery and more like a shock absorber built into the grid itself. Think of it as the difference between a GPS app that only shows your route and one that reroutes you in real time as conditions change. Grid-forming control is constantly adjusting, not just storing and waiting. This build-out did not happen by accident. National policy now requires new renewable capacity in China to be paired with storage, and Xinjiang has positioned itself to become a proving ground for exactly this kind of long-duration architecture at national scale. Dozens of similar pairings are already planned across the region as the template proves itself. What started as a single demonstration project has become the reference design other provinces are now studying before writing their own storage mandates. The engineers knew what the number would look like once the plant reached full output. The question was whether anyone outside the project would believe it without independent confirmation. Here is the honest picture. This is a genuinely large number, and it needed outside verification before anyone treated it as real. Global Vanadium Trade Association. Vanitech reported that project developer CTG confirmed the Jimisar facility had been fully commissioned and was running at full output. Not a projection, not a Phase 1 milestone, a completed and operating plant. Once verified, the scale becomes easier to translate. The facility is expected to enable roughly 1.72 terawatt-hours of renewable generation annually that would otherwise have gone to waste through curtailment. Enough electricity to meaningfully offset the output of a mid-sized fossil fuel power station for an entire province. The developer estimates this displaces more than 1.6 million tons of carbon dioxide every year, roughly equivalent to taking several 100,000 cars off the road. But this is where it gets uncomfortable, and it matters more than the headline number. Vanadium flow batteries are not going to replace lithium in your phone, your laptop, or your car. Their energy density is far too low for anything where weight and size matter. This is not a universal replacement for lithium. It is a replacement for lithium in one specific job: grid-scale, long-duration storage, where lithium was arguably never the right answer to begin with. That distinction matters because it is the difference between a genuine breakthrough and marketing hype dressed up as one. For Zhang Huamin, this plant is not just an engineering milestone. It is the answer to a bet he made in 2000 when almost nobody in the battery world thought vanadium was worth the funding. 25 years later, the chemistry he refused to abandon is running a Chinese province's grid at gigawatt-hour scale. Lithium did not get replaced. It got outcompeted in the one arena where it was never actually the right tool for the job. If that surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. What happens in one province does not stay in one province. The same long-duration storage problem exists everywhere the world is racing to build solar and wind faster than the grid can absorb it. Curtailment is not a uniquely Chinese problem. Grid operators from California to Germany to Australia lose meaningful amounts of renewable generation every year simply because storage cannot bridge the multi-hour gap between when the sun shines and when people actually need the power. In the United States, utility procurement programs, including projects selected by Central Coast Community Energy in California, have already begun specifying vanadium flow systems specifically for their multi-hour duration profile, not their energy density. That single design choice, prioritizing hours over density, is quietly reshaping how utilities write their next storage contracts. Adoption is not automatic, and here is what most people covering this story leave out. Vanadium flow batteries depend on a vanadium pentoxide supply chain that is smaller and more concentrated than lithium's, and the upfront capital cost of a stack remains higher than a comparable lithium installation before you account for lifespan. Siting also requires real space for tanks. This is not a technology that fits in a shipping container the way lithium storage often does. Utilities weighing this trade-off have to think in decades, not fiscal quarters, which is a harder sell to a board than it should be. Industry bodies are already tracking the shift. Vanatech and the China Energy Storage Alliance have both documented accelerating VRFB deployment as utility operators increasingly weigh multi-decade lifespan against upfront sticker price. That shift in how operators evaluate cost, spreading it across 30 years instead of judging it on day one, is itself a quiet change in how the entire storage industry does its math. The same underestimation happened with solar power. Photovoltaic cost per watt fell by more than 90% between 2000 and the early 2020s, a decline almost nobody in the energy industry predicted with any accuracy when the technology was still dismissed as a curiosity. The limit here was never political. It was a cost curve and a materials science problem, and both are moving faster than most of the industry expected. And if you want to see the other half of the pressure lithium is under right now, it is not coming from a battery built for the grid at all. It is coming from a battery built to solve lithium's problem on cost and raw material supply instead of duration. I already covered China's sodium battery breakthrough, and what that team pulled off using materials that cost a fraction of lithium is just as hard to believe. That one is worth your time. Here's the largest implication of everything you just heard. The world's renewable energy build-out has been quietly bottlenecked by a single unglamorous problem. What to do with clean electricity when nobody needs it yet, and how to release it hours later without losing most of it along the way. That bottleneck is now demonstrably solvable, not in theory, but in a commissioned plant moving real electricity through a real grid. And it is solvable specifically because one team refused to accept that lithium's rulebook was the only rulebook worth playing by. If you made it this far, you now understand more about grid-scale energy storage than most people who write about the energy transition for a living. What was actually proven here is specific and important. A chemistry the industry left for dead in the 1980s, refined over 25 years by a team that refused to compete on lithium's terms, now outperforms lithium at the one job lithium was never built for: storing enormous amounts of energy safely, for hours at a time, for decades without meaningful decline. Zhang Huamin spent a quarter of a century building a battery nobody wanted funded on a bet that grid storage needed its own chemistry instead of a borrowed one. The gigawatt-hour plant now running in Xinjiang is what that bet looks like when it finally pays off. A career-length wager settled in liquid electrolyte and steel tanks on a Chinese desert grid. If this changed how you think about what better battery actually means, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should grid storage always prioritize safety and lifespan over raw energy density, even when it costs more upfront? Or should falling lithium prices keep it the default answer everywhere, grid included? I read every single one. See you in the next one.